Okay. Good afternoon everyone. Today we will be learning about stereoisomerism. Before we start with stereoisomerism, we should know what is isomerism. Isomerism is a phenomena in which two compounds are having same molecular structure, same molecular formula but different structural formula, and those kind of compounds are known as isomers. Those isomers are again divided into two parts, and one of them is stereoisomerism. Now you can see here that isomers are divided into two forms. One is structural isomerism and stereoisomerism. The first one is structural isomerism. These are the compounds which have same molecular formula but different structural formula. These are further divided into chain isomerism, position isomerism and functional group isomerisms. Chain isomerism means if a compound is having 4 carbons, say for example in butane, then all the 4 carbons are arranged in single chain, a straight chain compound. And in another form of chain isomerism, 3 carbons will be arranged in straight chain and the fourth one will be perpendicular. So in case of chain isomerism, we have straight chain compounds and branch chain compounds. Next is position isomerism. These kind of isomerism is seen with compounds which have functional groups. Say we take example of 1-butanol and 2-butanol. So they come under the category of position isomerism. The reason for that is in 1-butanol OH group is on first carbon and in 2-butanol OH group is on second carbon. So those kind of compounds where the position of functional group is changing, they are known as position isomerism. Now the third one is functional group isomerism, which means the difference in the bonding of functional group to the carbon atom. Very good example of that is nitroethane. In nitroethane, in one isomer, nitrogen or the nitro group is bonded to carbon through nitrogen, and the second one is nitrosoethane. In that compound, nitro group is bonded to carbon through oxygen. Another example of functional group isomerism is seen in cyanides and isocyanides. In cyanides, the bonding is through carbon, and in isocyanides, the bonding is through nitrogen. So these all constitute structural isomerism. The second type of isomerism is stereoisomerism. The difference between structural and stereo is that the molecular formula again in stereoisomerism remains same, but the position of different atoms which are arranged to the central carbon, their position in space will change. So they occupy different positions in space. This again is further divided into two parts. One is geometrical isomerism and one is optical isomerism. So we'll start first with geometrical isomers or geometrical isomerism. Now geometrical isomerism, the first condition is that it is seen only with compounds which are having double bonds or triple bonds. With sigma bonds, geometrical isomerism is not seen. Now the difference in geometrical isomerism, the thing is that when you have two same atoms arranged to the central carbon atoms and the position of both the atoms or groups is same, then they are known as cis. You can see in the picture that the two green balls, they are two same molecules or two same atoms, they are on the same side. They are known as cis, and when the groups or atoms which are same are on the opposite side, then they are known as trans isomers. Now the reason for compounds with double bond and triple bond, what is the reason that they are showing geometrical isomerism and not the single bonds? The reason is that in single sigma CC carbon bonds, the rotation is very high. The carbon-carbon bonds rotate so high that you cannot identify groups coming on the same side and groups coming on the opposite side. But in case of C double bond C or C triple bond C, the rotation gets restricted and the carbon atoms rotates very slowly. And because of that, it's easy to identify groups coming on the same side and groups going on the opposite side. So if you want to identify cis isomers and trans isomers, that can be easily done with compounds having double bonds and triple bonds. So these are cis and trans isomers of different compounds. Now the physical properties of geometrical isomers, their physical properties maximum times remain same The only difference comes in their chemical properties. In physical properties, the difference is only in their melting point and boiling point. Next is optical isomers. Optical isomers means that the position of different atoms attached to central carbon is different, their position in space is different. Plus, optical isomers can be seen with compounds which are having 4 different groups. That means if a compound is having 2 similar groups, then optical isomerism will not be seen. Now, as you can see here, the structure of fluoromethane. So, the first one is the structure of fluoromethane and the second one is its mirror images. So, whenever we have any compound with its mirror image, maximum number of times the mirror image remains same. But in case of compounds which are having 4 different groups, for example in lactic acid, all the groups attached to central carbon atom are different. In this case in lactic acid, the mirror image is not same as that of compound. Their mirror image is non-superimposable. That means we cannot impose mirror image on the compound itself, and these kind of compounds which show these kind of images are known as optical isomers. Now, as I had said earlier that optical isomerism is seen with molecules or compounds which have 4 different carbons attached to it, and those kind of compounds are known as chiral compounds, and the carbon to which 4 different groups are attached, they are known as chiral carbons. And these kind of compounds which have chiral carbon, they are known as optically active compounds. And the optically active compounds are known as enantiomers. They can also be distinguished as RNS, that is rectus and sinister, depending on the rotation, or D and L. If we have a 50-50 mixture of both R and S or D and L isomers, then that mixture is known as racemic mixture, and the overall optical activity is 0. This is an example of propene-2-ol or 2-propanol, where we can see that 2 methyl groups are similar and therefore the compound is optically non-active. Next is example of 2-chlorobutane, and here we can see that all the 4 groups which are attached to central carbon, they are different, and therefore the compound is known as optically active compound or an enantiomer. Now, optically active compounds, as we can see enantiomers, their properties, physical properties are same, but the difference is only in 2 things, that is their effect on plane polarized light, and another is their interaction with other chiral molecules.
Okay, so let us discuss a new topic which is closely related to the earlier topic of polymers or macromolecules. We focus more on the polymers of natural origin or the biological origin, or the molecules of life, also known as biomacromolecules. So, for example, in case of a cell, you have several small organic molecules which join together to form a larger molecule, and this larger molecule is also known as a biomolecule. As we discussed earlier when we discussed polymers, macromolecules are large molecules composed of thousands of covalently bonded smaller molecular weight units, also known as monomers. Now, what are different types of biomolecules? So, there are 4 classes of molecules that are quite common, that is carbohydrates, proteins, nucleic acid, fats, and even vitamins. But out of these classes of organic molecules that are related to life, fats are not polymers, whereas carbohydrates, proteins, and nucleic acids, which are closely related to proteins or made up of amino acids just like proteins, are nothing but polymers or biomolecules or biomacromolecule, if I use that term. So, as we all know that one of the very common way of forming a large molecule is One of the common ways of forming a large molecule or a polymer is by dehydration reaction. So you have water molecule which is getting removed by a combination of two reactants or the monomers or the joining of these units by a covalent bond. A polymer can be disassembled by hydrolysis, which is reverse of the dehydration reaction. So for example, if you have a short polymer chain, you remove this molecular weight, so you have basically you remove this water molecule and you have a longer molecular weight compound which may be an oligomer. If you have many of such units combining together, it may result in a polymer. Whereas in case of a reverse thing, if you start with a polymer and if you hydrolyze it, okay, you can break that polymer here. So in case of hydrolysis, you have addition of a water molecule which breaks the bond. So what makes these biomolecules unique? There are a lot of diverse molecules that are available because of these various combinations of small molecular weight entities, and various variety of polymers can be built up from small set of monomers. So depending on the species and different types of species, you can have different types of macromolecules. Now let us discuss the first class, that is carbohydrates. So generally carbohydrate includes sugars and basically polymers that are made from sugar. Now in case of carbohydrates, the simplest of the repeating unit or the starting unit is a monosaccharide. Mono means single unit, saccharide is for sugar. So a carbohydrate that is formed by combination of various single sugars would be a monosaccharide, which then further combines to form a polysaccharide. So a polysaccharide is nothing but a carbohydrate, which is a large molecular weight compound which is formed from many sugar building blocks. So what is typical of these sugars? These monosaccharides have small molecular weights and generally consist of this type of multiples of CH2O. One of the common unit or the common monosaccharide is glucose, which is quite well known. And these monosaccharides are classified by the location of the carbonyl or C double bond O group and the number of carbons that are present in the carbon skeleton. So depending on the number of carbons, you can have a 3 carbon chain, also known as a triose sugar. You have 5 carbon saccharide, that is a pentose sugar, and you have a backbone with 6 carbons, very common in case of glucose, galactose or fructose. So a lower molecular weight 3 carbon compound like glyceraldehyde can result in a triose sugar, whereas a comparatively higher molecular weight 6 carbon monosaccharide like glucose can result in various different polysaccharides. So what are the functions of these monosaccharides? These monosaccharides are important source of fuel for the cells and also serve as the raw material for the building up of the molecules of a cell. Quite often we draw them or illustrate them as linear skeleton, but in reality when you form the aqueous solution, they form rings. So in case of a linear saccharide, monosaccharide, it will look like this, whereas you may have a ring structure which is shown here. There is another term, a disaccharide. So di indicates 2 and saccharide, so basically a combination of 2 monosaccharides resulting in a disaccharide. and the linkage or the covalent bond which binds or holds this together is known as a glycosidic bond. So, for example, if you have a glucose reacting with a galactose, you have formation of a lactose, whereas you have two glucose units combining through a covalent bond or a glycosidic linkage, you have formation of maltose, whereas a cane sugar will be formed by reaction between glucose and fructose, which is linked through a glycosidic bond. So, here you have two glucose molecules which are reacting to form various different disaccharide. Say for example, you have glucose plus fructose forming a sucrose, okay, whereas glucose molecules reacting to form maltose, and if you have glucose and lactose, you have formation galactose, you have formation of lactose sugars. Obviously, the next step is polysaccharide. Poly means many, saccharide again is known is for sugar. So, polysaccharides can be said to be or defined to be the polymers of sugars. Now, these polysaccharides have two important roles, that is of storage of information and structural role. So, depending on the structure and function of a polysaccharide, or depending on the structure and function of the monomer, the role of a polysaccharide can be determined. Now, starch is a storage polysaccharide which is present quite commonly in plants and mostly made up of glucose monomers. So, the plants store this surplus starch as granule within chloroplast and other plastids. So, for example, you have starch here in the center and on the periphery you have chloroplast, and starch is mainly made up of two important sugars, that is amylose and amylopectin, whereas glycogen is a storage polysaccharide in animals. In humans and other vertebrates, glycogen is stored mainly in liver and the muscle cells. So, you have these clusters or granules of glycogen which is present in case of the vertebrates. Now, cellulose is a major component in plant cells. Just like starch, cellulose is a polymer of glucose, but here the glycosidic linkage differ. The difference is based on the two rings formed by glucose. One form of glucose is known as the alpha glucose and another form of glucose is known as the beta glucose. So, depending on this linkages, this here is an alpha glucose whereas this is a beta glucose. Depending on this reaction at this position or this position or the alpha position, you can have a 1,4 linkage in case of an alpha glucose, that is quite common in case of starch, whereas you can have a beta glucose linkage in case of a cellulose. So, what are the typical features of polymers that are formed by this type of linkages? When you have an alpha glucose, generally you form a helical polymer, whereas in case of a beta glycosidic linkage, a polymer is formed which is straight. So, in case of a straight structure, the hydrogen atoms on one strand can bond with the hydroxyl groups of the other strands. In case of the cellulose molecules, these are held together into microfibrils, and this form very strong building materials for plants. Say for example, here these are polymer molecules are entangled into this microfibrils where you have a beta linkage. So, there are enzymes that digest the starch by hydrolyzing these alpha linkages, but they cannot hydrolyze the beta linkage in cellulose. In case of human beings, the cellulose in the human food passes through the digestive tract as a insoluble fiber. Some of the microbes use this enzyme to digest the cellulose, and there are examples like herbivores like cows to termites. They have a symbiotic relationship with some of these microbes. So these microbes have this type of microstructure. There is another class of polysaccharide known as chitin. Chitin provides structural support for the cell walls of fungi. This chitin has a very important role as a surgical thread. The typical structure of a chitin is like this, and here you have a surgeon using this chitin as a surgical thread, and these are very flexible materials. Most importantly, they are of natural origin, and that's why this surgical thread here will decompose once the wound or the incision in a patient undergoes healing, and in that